Okay, guys, so this is going to be one of those units that kind of goes in like a lion and comes out like a lamb, or the other way around, goes in like a lamb and comes out like a lion. What we're going to do today is we're going to establish a common vocabulary. This is going to kind of be like going to the MTC as a missionary. This is similar only in the world of electrochemistry, because before you can effectively communicate a message, you got to know the language, right? Now, the problem is this, and I know that some of you have friends or relatives or siblings that have been on missions, and you've probably heard this before, that people that are out in foreign language speaking missions will tell you that the day, and many of them can tell you the day that they realized they were finally becoming fluent in that new language was the day that what happened? Not thinking, dreaming. Yeah, it's the day that you start dreaming in that other language that you realize that you're no longer a primary English speaker. Well, guys, similarly, part of what you need to do is take these two terms, and the word for what we're talking about is called automatize. If you're not familiar with the concept of automatize, you guys, I think most of you drive, and you remember the first day you got behind the wheel, right? And you're like, oh crap, and you're aware of everything in the car. You've got 10 and 2, although they don't teach that anymore because when the airbag goes off, it blows your arms off. So now it's down here. But you're aware of your hands. You're aware of all the levers and the knobs and the buttons, and hopefully not your cell phone. But you're hyper aware of everything in the car. But for those of you that have now been driving for a couple of years, you drive home this afternoon and you have no idea how you got home. You've had that experience, right? Yeah, you pull into the driveway and you're like, crap, how'd that happen? Guys, the same thing has got to happen here. These two terms, oxidation and reduction, have got to be automatized. So what we're going to do to start the day is we're going to define these terms, and then I'm going to give you some cheesy little ways to remember these things. Hannah, you're probably going to tell us about oil rig, right? Because you learned that, yep. And so that's the way they like to do it at the U. They like to talk about oil rig. I have another way to do it. But guys, the bottom line is this. Very, very quickly, you have got to stop thinking about this and just be able to look at a balanced equation and go, oh, look, that was oxidized. Oh my gosh, that was reduced. And especially as it applies to batteries, which we're going to talk about next time, this has got to become automatized. And in the same way, guys, that when you go into the MTC, they just throw you to the dogs and you start speaking Spanish and you're just around Spanish-speaking people from day one, because the way to learn it is to actually immerse yourself in it. Guys, that's the trick with this too. But how do you immerse yourself in something in this class? Homework, right? That's where you get your immersion experience. So guys, it's going to be critical that you're drinking deeply of this homework, because very quickly you've got to have robust ideas of what oxidation and what reduction mean. You okay? Okay, so with that said, guys, what we're going to do is we're going to do some language lessons, and there are going to be some details here that you're going to want to keep very careful track of, and obviously I'll highlight those for you. And then, guys, you're going to hate this. You get to learn to balance oxidation-reduction reactions. It's hell. It's horrible. Just trust me, you're going to hate it, but you get to do it anyway. So, I would like to point out, though, that I've been balancing redox reactions in public for, this is my 14th year of AP Chemistry, and last year was the first year that I balanced 2 redox reactions without making a mistake. Every other year, I have made it, and not trying to, I've made at least one mistake. Last year was the year, and here's the thing that's funny. I've been balancing the same 2 redox reactions for 14 years. And I still can't do it. You'll see. It's amazingly detail-oriented. So guys, let's get started. When we talk about oxidation reduction, which was the title of your notes, you should know right up front, guys, that there's a shorthand, maybe. So we have oxidation reduction, right? But we switch them and reduce them, and we call them redox. So reduction and oxidation. So we could say oxidation reduction. Guys, just let me tell you, it sounds stupid to say reduction oxidation. Don't do that. So if you're talking about these, make yourself sound smart and either say oxidation reduction or redox. Those are the two languages. In either case, guys, these reactions refer to a transferring of electrons. Now, guys, this leads to a problem. The problem that we run into is this, and you probably have a sense of this from having read chapter 20. Oxidation means losing electrons. Reduction means gaining electrons. We'll write that down again in a minute. But guys, what we have here is an exchange of electrons. The problem is we can't see electrons. And yet, we've got to be able to track electrons through chemical processes. So guys, in the same way that we've never seen a black hole, you know that, right? That's why they're called black holes. Because the only things that we can see in space are things that give off light or things that actually light can travel through and filter out some of the wavelengths. Remember when we talked about emission and absorption spectra? Those are the only things that we can see in the heavens. So how do we know that black holes exist? It's not the absence of light, because there's a lot of black places in space too. How do we know that black holes exist? Secondary evidence. We can see whole galaxies disappearing, being sucked into nothingness. And so we can go, oh, there's a black hole, because we don't see the black hole, but we see the black hole affecting something else. It's secondary evidence. Guys, similarly, we can't see electrons, but what secondary evidence do we have that would tell us that electrons are being transferred? Changes in charge. So guys, when we look for oxidation reduction processes, we can't see the electrons move. So the evidence that we use is we can see the charges or the oxidation states of the elements changing as they are oxidized or reduced. Okay, so guys, with that said then, let's finally define some terms. What does it mean if something is oxidized? What is happening to it? It is losing electrons. Guys, oxidation refers to a loss of electrons. And then guys, conversely, reduction refers to a gaining of electrons. And maybe I should have put these bullet points in the other order, because this then becomes the overriding principle. That when oxidation reduction takes place, when redox takes place, the electrons are transferred from the atom that is oxidized to the atom that is reduced. The thought then being that the thing that's oxidized loses electrons, and the thing that is reduced gains electrons. So guys, once you're caught up with that, we're going to talk about all of the ways, all the tricks. Well, not all of them. It's not exhaustive. But we're going to talk about some ways that you can remember that oxidation means losing electrons and reduction means gaining electrons, and how to keep that straight. So let me know when you're caught up, and then we'll talk about it. You guys all okay? Are we good? So guys, I would suggest to you this. If you really want to understand that oxidation means losing electrons and reduction means gaining them, maybe it would be helpful to understand why we call losing electrons oxidation in the first place, and why we call the gaining of electrons reduction in the first place. So where do the names come from? Why do we call losing electrons oxidation? Not usually, but why make the connection? What does oxygen do to metals? It makes it rust. And we'll talk more about that in a minute. But what is happening to those metals when they rust? They're losing electrons. So guys, we'll write a balanced equation in a minute. But guys, the bottom line is this. In the 18 whatevers, when they were beginning to understand this idea of oxidation and reduction, the place that oxidation and reduction is most obvious, as Dan pointed out, is in the rusting of metals. And they discovered that when metals rust, they are actually being reacted with oxygen. And what that oxygen is doing is it's pulling electrons off of the metal atoms. And so they said, this is a phenomenon that is taking place in the presence of oxygen, so they called it oxidation. So guys, maybe it's helpful if you see this. Why would oxygen be good at oxidizing metals? It's got two places to put electrons, and it's got a high electronegativity. So oxygen is good at oxidizing things, in that case metals, when they originally coined the term, but that's where oxidation comes from. Now, Taylor said something interesting. I said, why do they call it oxidation? And he says it usually involves oxygen. And guys, that's not true. There are billions of oxidation reduction reactions that have nothing to do with oxygen. We call it oxidation because that's the term they coined when they originally identified the process. You get the idea? Is that okay? All right. So with that one done, let's tackle this one. Why do they call reduction, let me say it differently. Why do they call gaining electrons reduction? Exactly. It makes the charge of the atom go down, right? What's the charge of electrons? Negative. And so when you gain electrons, what happens to your charge? It goes down. It could go from positive to 0. It could go from 0 to negative. It could go from negative to more negative. It doesn't matter. In any case, as you gain electrons, the charge goes down. So with those two things in sort of the back of your noodle, guys, this is the way that I keep them straight. You ready? Well, originally. Now I just know them because I speak the language. But initially, this is the one that I liked. I just remember the charge of the atom that is reduced is reduced. It's redundant and catchy enough that it's stuck in my head. So the charge of the atom that is reduced is reduced. But Hannah has one for us that's even catchier. Oil rig. Oxidation is loss, reduction is gain. And clearly this is better than mine because this came from a university and I'm just a lowly high school teacher. Do you have any others? No? You don't lay awake at night thinking of things like this? So, guys, however you want to tackle it, the bottom line is this. And again, relating this back to missionaries. When a missionary first learns to speak a language, they translate. You know, hi, my name is Larry. Yo me llamo Larry. But they think at first in English, then they translate, then it comes out of their mouth in broken Spanish, right? But before you start dreaming in Spanish, there's also that moment where you stop saying it in English and then internally translating, right? That's where you've got to get pretty quickly. You don't want to be thinking oil rig. You don't want to be thinking that the thing that's reduced is reduced. You don't, quickly you've got to get out of that and just go, oh, that was reduced. So, guys, push yourself to get to that place as quick as you can. So, however you choose to do this, this is important for you to understand. You can't have one without the other, right? In the same way that you can't have an acid without a base. Because what is fundamentally a Bronsted-Lowry? Fundamentally, guys, what is a Bronsted-Lowry acid-base reaction? An exchange of protons. And if one's the acid, the other one's the base, right? If somebody's giving away protons, they've got to go somewhere, and the somewhere we call the base. Well, guys, similarly, you can't have oxidation without reduction. If the thing that's being oxidized is giving off electrons, they can't just dance in free space. They've got to go somewhere. And the place that they go is then, by definition, the thing that's being reduced. So you can't have one without the other. You okay with that? Okay. So now, guys, this is where this starts to get ugly. We now understand that these have to happen in pairs. Actually, I didn't want to go quite that far. We now understand that these have to happen in pairs. But the problem is this. Not the problem. The additional complexity is this. Let's try this. Here's an atom. If it's oxidized, what happened to it? Loses electrons. Where do they go? To the thing that's being reduced. Now, guys, watch over here, my finger, the thing that's being reduced. What did this guy do to this guy? Oxidized him, right? So let's think about, so what we're saying is this. The guy that loses electrons is being oxidized. The guy that gains electrons is being reduced. But we can also change the focus, and we can say, if this guy is oxidized, he gave electrons to this guy, but now if we turn our attention to this guy, the guy that's been reduced can also be thought of as the guy that oxidized this guy, right? And similarly, if this guy is being oxidized, what did he do to this guy? Reduced him. And we call that the concept of agency. An agent is something that does something to somebody else. And so, guys, now what we need to do is talk about this idea of agency. Because these happen in pairs, the thing, and here's the summary, the thing that's being oxidized can be thought of as reducing the other guy. And the thing that's being reduced can be thought of as oxidizing the other guy. Do you see the nuance there? So, guys, it comes down like this. So the atom that removes electrons from another, think about that. The atom that removes electrons from the other can be thought of as the oxidizing agent. Why? Because it's oxidizing the other guy. See why it's so important to understand these terms reflexively? So, guys, the thing that is removing electrons from the other guy is causing oxidation in the other guy. But what is happening to that atom? It is being reduced. So now we've got two ways of thinking about it. We can think about what's happening to this guy, or what is this guy doing to the other guy. Now, guys, I bring this up because we're going to spend a whole day on this. We are going to spend a whole day talking about who reduces who oxidizes who. For now, I just wanted to lay the concept at your feet that we sometimes will focus on what's happening to an atom, other times we'll focus on what that atom's doing to another guy, and that's when we talk about the concept of agency. So, similarly then this, the atom that has electrons removed from it is causing oxidation in the other guy, right? So it is called, it's called the reducing agent because as it gives away electrons, it's reducing the other guy. So the guy that's losing electrons is causing reduction in the other guy, so we call that the reducing agent, but it itself is oxidized. Have I got you all spun around? Exactly. The agents do the opposite. Yep. Because if you're losing electrons, you're oxidized, but you're reducing the other guy. And if you're gaining electrons, you're being reduced, but you're oxidizing the other guy. It's this whole idea that they have to happen in pairs. You okay with that? You're good? Okay. So guys, I would propose to you that you don't need to write down what's coming next. This is sort of foreshadowing for what we're going to do for the rest of this year. Wow. So it goes like this. And again, please don't write these down. You don't need them in your notes. When we talk about oxidation reduction reactions, guys, what you're going to find out is that most of these are spontaneous processes, which, as you know, means that they tend to be exothermic. What you're going to find out, though, is that many of them are equilibrium processes, and eventually they run to equilibrium. You'll find out on Monday that that's when batteries die. That an oxidation reduction reaction is a battery, and when a battery dies, it means it's reached equilibrium. It's flowing in both directions simultaneously, which means it's not producing a current, and the batteries become dead. We'll get there in a day. So guys, in addition, and I just mentioned this, we can actually take these oxidation reduction reactions, and by separating them, we can get these things to produce useful current, which we call electricity. Now guys, we are going to study these things in three contexts, but what you've got to understand is that if we draw these things in a non-spontaneous way, we can actually apply a current and make them happen. This is what's called a battery charger. Guys, that's what a battery charger does. A battery has got a spontaneous direction. As it's going in that direction, eventually it reaches equilibrium. The battery's dead. So what do we do to recharge it? We hook a battery charger up to it, drive it in the non-spontaneous direction, which resets the equilibrium, and then it can function as a battery again. Oh, I wouldn't even pretend to go there. You're going to see, Taylor, and I'm going to be very candid about this. What I understand about redox chemistry, I can build batteries, and guys, let me just lay this on you. If you want to find a fascinating and wildly profitable career in chemistry, build batteries. It's seriously nutty. Why is it that batteries don't hold charge over time? Why is it that, well, these don't. These are lithium polymer batteries. But do you guys remember when, you probably don't, when phones used to have NiCad batteries in them? And they have a memory. And so it used to be that if you didn't fully drain your battery, so it's like if your battery could cycle like this, and if you were plugging it in every night, if this is dead, if you only drained your battery to here and then recharged it and went to here, eventually your battery would lose all of that power storage. And once your battery got to the bottom of where it was used to being recharged, it would die at that point. Are you guys even familiar with what I'm talking about? It's called memory. The lithium polymer batteries don't experience that, but it brings up two great questions. Why do batteries have memory, and why do lithium polymer batteries not suffer from that? I have no idea. The chemistry behind that is mind-boggling. And you guys understand this, right? Batteries are the thing right now that are crippling our society. You know that, don't you? Do you understand this? It's really cool, and maybe we could watch the video after the AP test. Guys, they actually got together a consortium of the brightest minds in science, economics, and sociology. They gathered all these people together in a room. It was fascinating. They videoed it. This was about 5 years ago. And they asked these people, and guys, these are Nobel laureates, these are heavy hitters. And they asked these people, what are the three greatest challenges that are facing the world? Not the US, not wherever they were from, and this was an international gathering. What are the three greatest challenges that are facing the world in the next 100 years? And I mean, it was disease, starvation, energy production, all of these things, right? Overpopulation, all of this stuff. And they just literally started writing these things down on the board. And then they said, what do we do about it? And this group of people actually realized war, everything. Guys, they realized that the answer to all the problems on the earth can all be solved if we can figure out a way to cleanly produce and store energy. It's crazy. Well, why is there starvation? Because there's not enough food. Why is there not enough food? Because there's not enough water. Why is there not, and you get the connection, right? We can't irrigate. There's enough land, and we could be farming. The problem is we don't have water. Why can't we get water to the fields to produce the food? Because we can't pump it. The water's there, it's just not in the right place, and if we could come up with enough energy to pump it where it needs to be, we'd have enough food. What about wars? Depending on where you stand, Democrat or Republican, why is the United States involved in all of the wars and skirmishes that we're involved right now? Some people would say we're fighting over oil, right? I don't agree, but I'd like to believe it's more than that. But guys, they would argue that the solution to all of this is energy production and storage. Now, the problem isn't the production. We can make power like crazy. Guys, we got wind, we've got tidal, we've got geothermal doesn't count. We've got solar. We have all of these amazing ways to produce energy. What's the problem? The wind doesn't always blow, the tides don't always move, and the sun doesn't always shine. And we've got no way to store it. That's the problem, guys. We have got intermittent power sources that could solve all the world's power problems. We just can't store it. And so, guys, if you want to get in, and why don't we have electric cars? Because we don't have batteries that are good enough. I mean, right now there's only one car company on the planet that is building cars. I actually saw one for the first time a couple of weeks ago. There's only one car company on the planet that's actually building cars that are a legitimate replacement for a family car. Right now you've got the Nissan Leaf and the Chevy Volt and the Prius and all these other cars. But guys, understand that every single one of those cars, with the exception of the Leaf, has a backup combustion engine. And the Leaf will only go about 35 miles and then you're dead in the water. You're done. Is it the Leaf or the Volt? Maybe it's the Volt. But guys, right now the problem is you can only go about 30 miles on battery power and then you're stuck. So do you guys know about Tesla? Yeah, there's this car company called Tesla that has actually created cars that have cruising miles, fully electric. There's nothing combustion, no gas tank. And they'll go 250 miles on a charge. So they are a legitimate replacement for combustion engine cars. The problem is they start at 60 grand. Yeah. Yeah, and that was the thing that was really funny. I don't know, Taylor said, hey, he's seen them before. I saw a Tesla. Do you know they make two different versions? They have the S and the R. The Tesla S is a sedan, and the Tesla R is a roadster. Oh my gosh, the Tesla R is so cool looking. And I don't know if you know how this works, but in fully electric cars, there's actually an electric motor at all four of the wheels. And I don't know if you know about electric motors. The torque that electric motors can create is off the charts. The Tesla R goes 0 to 60 in less than 3 seconds. Yeah, apparently it's like bordering on light. You step on the gas and you're just done. It's like there's no gears. They don't shift. I don't know if you know that or not, because these electric motors can spin so fast that there's no gears and they create so much torque off the bottom that you step down on the accelerator and you're 0 to 60 in 3 seconds. Yeah, it's crazy, but it's nutty. But so here was my Tesla S experience. I'm driving home from Salt Lake, and you guys know one of the differences between guys and girls, right? Guys are hyper aware of cars. I don't know if you know this, but it doesn't matter who you are. If you're a guy, you can't drive down the road. I could be driving with any one of you in a car, and I could go, hey, what's that? And you go, oh, that's a Chevy Tahoe. Guys just know about cars. My experience has been girls not so much. And maybe that's wrong. But I'm driving down I-15 and there's a U-Haul truck, right? And this U-Haul truck, it's not that big. It looks like a college student headed home for the summer, is pulling a flatbed dolly truck with a car on it. And it's a Tesla S. And it just looked totally out of place because you've got this picture that is probably going to be some like 22-year-old headed to his first job. You know, he's got his dog up front with him. And you know, you just sort of get a picture of who's going to be driving this U-Haul. And then he's pulling a $60,000 fully electric sedan behind him. It looked No, I know. It was completely out of place. I kind of liked it. But anyway. So, all right. So why are we talking about this? I don't know. No, it's good. Okay, so anyway, guys, here's what you're going to do. You are going to graduate from Orem High. You are going to go to college. You are going to get a degree in chemistry or chemical engineering. Then you're going to start building batteries, and you are going to become a multi-billionaire. And then when all of that happens, you're going to hearken back to this conversation, and you're going to come back and write me a fairly sizable check. And understand the size of that check will be a rounding error in your checkbook, and it will probably triple my yearly income. And just as a way to say thank you. Shall we? Just saying.
This is your school fee.
No, this is the this is paying it forward. That's right. That's right. So guys, this is where we're going to go with this. We're going to talk about batteries. We're going to talk about electroplating and corrosion. But today what we're going to do is just make sure you understand the big picture. So in order to do that, what we need to do is we need to bring you back to looking at reactions that are redox reactions. This is actually right out of the notes. You remember our second unit? Remember we did that really quick unit? Well, no, it was our first unit, second chapter. We did chapter 5 over aqueous chemistry, and we touched lightly on acids and bases. We touched lightly, well, actually not lightly, we touched deeply on precipitation and solubility. And then we touched lightly on redox. And I said, guys, when we come back to this in mid-March, this will be the last unit of the year. That's today. Isn't that weird? So guys, consider this. Put it in your notes. You really want to do this. Now, I'm not saying that because I think you do. I'm telling you that because you need to. You don't need to. I mean, well, you know, no, I take that back. Yes, I would, because it's significant. Because this will actually help you maybe begin to see something that is common to oxidation reduction reactions. So guys, I'm just going to tell you up front, this is an oxidation reduction reaction. Because that's true, what do you know must be happening in this reaction? Electrons are moving, right? Again, like the black hole, what evidence do we have of electron movement? Changing in charge or oxidation state, which are functionally the same for us. So we need to assign oxidation numbers to these. We did this in chapter 5. Let's remind ourselves and do it together. What is the oxidation number of an atom in its elemental state? 0. Now, hydrogen is +1 and chlorine is -1 off of the periodic table. Now guys, chlorine holds its -1 charge, making zinc what? +2. Are you all okay with that? And then guys, what is the oxidation state of hydrogen? Both of them? Yeah, this is right. Hydrogen's diatomic. This is the elemental state of hydrogen, so it is 0. Okay, so now guys, from there, this is the way that I like to do this. We need to find the changes. Whose charge changed? And we know that it's got to be 2, right? So zinc starts at 0 and goes to +2. So it changed. So I like to do this. Now guys, what about the hydrogen? Did hydrogen change? It went from 1 to 0, so it changed. What about the chloride? It didn't change, making it Taylor what? Yep, I heard you say it under your breath. Guys, it's a spectator, right? Started at -1, ended up at -1. It's aqueous in both cases. We would have given, remember when we talked about net ionic equations? It's a spectator. Okay, so now guys, we understand, well, not understand, we've identified who changed. Zinc changed and hydrogen changed. So now what we need to do is talk about how they changed. So guys, zinc went from 0 to +2. Relative to electrons, what had to happen to zinc? Oh, good, you cut out the middleman. It must have lost electrons, which means it is oxidized. Good. So we can just put OX. Let's just put OX. That guy was oxidized. Now that we know that zinc is oxidized, or I'm sorry, yeah, zinc is oxidized, we know that the other guy's reduced. But let's make sure. So guys, hydrogen starts at +1 and it goes to 0. What is it that would cause hydrogen's charge to go from +1 to 0? Gaining an electron. And gaining an electron causes the charge to go down. We call that reduction. So this is the one that is reduced. You okay with that? Okay. Now guys, we've got to do some accounting, because you understand the idea that you can't have oxidation without reduction and vice versa. But you're going to find out that not only can't you have one without the other, you can't lose electrons. The balance sheet has got to work out where all the electrons that are lost have got to be gained. So guys, zinc goes from 0 to +2. How many electrons did it lose? 2. So we're going to write that down. This lost 2 electrons. It's really important, guys, that you can identify that. Now, what happened to hydrogen? Well, hydrogen went from +1 to 0. So how many electrons did hydrogen gain? 1, but there's 2 hydrogens for a total gain of 2 electrons. Do you get the idea? Okay. So guys, with that as a fundamental background understanding, I need to ask you some questions, and I want you to write down without speaking. I want you to write down your answers. And literally, I want you to write these down, because you will have to write these down on the test. You ready? Given what we just wrote, and guys, trust me on this, you've got to write this down. I know you're thinking, I didn't write this down. In the same way that when some of your teachers say close your eyes and imagine, you don't close your eyes because you think it's stupid. I'm that guy. I do. And guys, when they say, everyone get up and clap, I don't clap. It's just not me. But you got to do this. So guys, here's the question. Which substance is oxidized? Write down your answer. Write down your answer. Which substance is oxidized? You got it? Question 2. Which substance is reduced? Write down your answer. You got to commit, guys. Question 3. How many electrons are exchanged? Is that James sending a picture of him and Mickey? Be a nice touch. Okay, guys, you ready? Let's go over your answers. Which substance is oxidized? This would be an acceptable answer, or this would be an acceptable answer. Got it? So zinc is oxidized. Which substance is reduced? Only one of you got it right. Guys, if on your paper, answering the question, which is reduced, you have this or you have this, you are wrong. Hydrogen is not reduced. Hydrogen ion is reduced. And now you're going, that's stupid. Guys, if you don't understand that hydrogen and hydrogen ion are not the same stinking thing, you've got issues. Because, guys, in the same way that sodium and chlorine are not the same as sodium ion and chloride ion. Guys, what's sodium? A shiny combustible metal. What's chlorine? A brown deadly gas. But what happens when we take away an electron from sodium and give it to chlorine and form sodium ion and chloride ion? It's delicious. Guys, and delicious is different than combustible and brown and deadly. Gaining and losing electrons radically changes the behavior of the atoms. So, you need to understand that hydrogen is not reduced. Hydrogen is the product of the reduction, but hydrogen is not reduced. You ready for this? Hydrogen can't be reduced. Why can't you reduce hydrogen? Its 1s sublevel is full in both atoms because of the sharing of electrons in that sigma bond, and you can't reduce hydrogen. It's impossible. Okay? So guys, the thing that's reduced is hydrogen ion. And then question 3, how many electrons were exchanged? 2. What if the question said how many moles of electrons are exchanged? 2, right? Because this could be atom to atoms to well, not molecule, formula unit to molecule, or it could be moles. So it's 1 mole of this, 2 moles of this, 1 mole of that, 1 mole of that, and then it would be moles of electrons. And that's the way we're going to talk about them in coming days. You get the idea? Y'all understand that hydrogen is not reduced? All right, guys, here we go. This is about to get a little bit crazy. All right, one more thing to do. You get to learn to balance redox reactions. The only thing that makes this worse than childbirth is some of them take more than 9 months. These are horrible. Seriously. Yes. You know.
I don't know about childbirth, but I have balanced redox.
That's right. That's right. That's right. So, guys, it used to be back in the day when the AP chemistry test was more predictable. Question number 4 on the AP test, you may know from looking at older exams. Question number 4 used to be balancing equations. They used to give you 7 and you had to do 5. Then they narrowed it down to 3 and you had to do them all and then answer a follow-up question. Now it's gone away altogether. With that said, the advice used to be this. When you get on question number 4 to the redox reaction that they want you to balance, skip it. Because you're going to get it wrong and it's going to take more time than it's worth. So that was the advice. Skip it. Doesn't mean I didn't teach it, it just meant skip it. Guys, now we're still going to learn it. If it's on the AP test, we have no idea where it's going to be, but it could be out there somewhere. So guys, it goes like this. Please don't write this down. Up until now, guys, when we have balanced equations, remember we've always been in the back, maybe not, but the fundamental reason we balance equations is the law of conservation of mass. If it goes in, it's got to come out. Well, guys, now we have something else that we've got to consider. This isn't officially a thing, but there's actually a law of conservation of electrons. In the same way that we can't gain or lose mass, we also cannot gain or lose electrons. Understand that there is not officially a law of conservation of electrons, but the concept holds true. So, how do we balance oxidation reduction reactions? You ready? Write this down. Steps. Remember how you used to love in general chemistry steps? Let's solve a percent yield problem. Step 1, write a balanced equation. Step 2, start with the mass of a reactant. Step 3, set your goal at the mass of the known product. Step 4, solve. Step 5, use the, you know what I'm talking about? And you know that that's the thing that made AP chemistry a lot harder, is all the steps went away. Here's steps. Step 1, guys, write half reactions. You don't know what they are. I'll teach you in a minute. Then, guys, step 2, balance the redox equation. Here's the steps. Step 1, balance all the other elements. Step 2, balance the oxygens by adding water. Step 3, balance the hydrogens by adding protons. Step 4, balance the charge by adding electrons to the side with the greatest overall positive charge. Step 5, multiply each half reaction so that the electrons balance. Step 6, add the two half reactions together and simplify, and then check your work. Well, step 7, if it's in a basic environment, add hydroxide to both sides to get rid of the excess protons. Then step 8, check your work. Then step 9, curl up into a ball and weep like a child. Oh boy. It is actually, yeah. Yeah, and you're going to find, Taylor, that that's an interesting parallel, because what you're going to find is that we're going to do these very much in lockstep, and you'll see it'll help you keep things organized. Guys ready? Me neither.
Can I assume the fetal position?
Sure. So guys, for those of you that are not in my lab class, I need to prep you for this. So on Monday in class, my 10-year-old daughter is going to be here. I already shared this with my lab folks. She's been begging me all year to come to class, and I finally relented, and her 4th grade teacher said the best time to come would be on on a Monday, and we picked next Monday. So we're gonna have an overly anxious 10-year-old girl floating around the room. I think of that because we were talking about curling up, and then Taylor said the fetal position, which is actually how my daughter likes to sleep. And my daughter has a great appreciation for laps. She loves to sit in people's laps, especially mine, which is now kind of uncomfortable because she's 10 and large. But she likes to be in a fetal position so much that her nickname is Nugget, because she gets in nugget position and likes to be in that position. And about a year ago, she was all curled up in my lap, and we were having one of those sort of magic moments, and we were sort of talking about life. And I looked down at my daughter as she was sort of looking up at me, and remember, she's 9, right? And I said, Jessie, I don't want you to ever grow up. And she looked up at me and she said, Dad, pretty soon I'm going to have babies.
Slow down, wait a second. Slow down. You got like at least 10 years. You better at least 10 years.
So I went into my basement and loaded my shotgun and yeah. Although it's interesting, my daughter, she just has such a natural draw towards kids, like little kids. Like, you know, at our church we have a lot of things going on in the evenings and Sunday mornings, and it's really like taking candy away from a child when I tell my daughter that she can't work in the nursery. She just so much wants to be around little children that she's going to be a great mom someday. But yeah. All right, you guys all caught up? Yeah, but not soon. Okay, guys. So this is the piece that you're missing, right? We don't know how to write half reactions. So I'm going to teach you. I would encourage you not to write this down. But watch. So guys, these are half reactions. You ready? First of all, where does the name come from? Well, if you take two half reactions and put them together, what do you get if you add together two halves? You get a whole, right? You get the whole oxidation reduction reaction. But you already understand that every oxidation reduction reaction has to be an oxidation and a reduction. So we call these half reactions because one of them represents the oxidation half and the other represents the reduction half of the reaction. Now guys, the important thing, the thing that makes these tricky is the way that you write them. Again, please don't write this down. So guys, when we talk about half reactions, we're talking about isolating the oxidation and the reduction process. So, do you see the connection with what we talked about 10 minutes ago? Do you see that this is the same reaction? What's the difference? Chlorine's gone, which makes this what? The net ionic equation. Now guys, the idea is this, and I'm asking you not to write this down because it's already in your notes. So zinc was oxidized, hydrogen was reduced. Hydrogen ion was reduced. So guys, the question is this. We understand that zinc is oxidized and hydrogen ion is reduced. So let's talk about what that means. What does that mean happened to zinc? Lost electrons. What does that mean happened to hydrogen ion? Gained electrons. Now guys, here's the problem. In your mathematical mind, you think of losing as being a subtractive process, right? And you think of gaining as being an additive process. Here's the deal. When you write these as half reactions, we are going to write both of them in a positive context. Let me show you what I mean. The reduction is easy. So, again, you don't need to write these down, but the idea is this. Taking these hydrogen ions, what happened to them? They gained 2 electrons and they became H2. Yes? Okay, that's great. Now notice this subtlety. Guys, we could say correctly this. Zinc minus 2 electrons produced zinc 2+. Isn't that really what happened? The zinc lost 2 electrons and became zinc 2+. Here's the problem. When we write it that way, electrons appear to be reactants in both processes. But now you're thinking to yourself, wait, I've never seen a chemical equation with a subtraction. You ever thought about that? You haven't. You've never seen a chemical equation with a subtraction. So now what we need to do is find a way to write this without the subtraction. So what do we do? Add the electrons to both sides. And we think of it like this. Get it?
We think of it as a dissociation or a decomposition. So zinc atom turns into zinc ion, and when it does, it loses 2 electrons. But we represent the loss not as a subtraction, we represent it as a product. You understand the difference? And guys, that difference, while it seems subtle, is important, because again, we never have subtractions in balanced equations. So fundamentally, this is bad form, but the underlying idea, and again, let's talk about it, is this oxidation or reduction? This is reduction, electrons are a reactant. This is oxidation, electrons are a product. Do you see the difference? Go ahead. No, not until they get together. When these things happen together, well, in this case, not at all, because that's a strong electrolyte, so no. In this case, even when they get together, sometimes when they get together it could be, but now no, because this is a strong acid, so it wouldn't be. Yes, I see what you're moving forward. Yes, that's true. Yeah.
So your main reaction is just squishing those two together and then we get electrons.
Right. And so you could do that, right? You could go this. You remember how, like Hess's law, we bring all the reactants together and we bring all the products together? If we did that, we'd get 2H plus Zn plus, or plus Zn plus 2 electrons gives us products Zn2 plus and, oh, I should have gone here, Zn2 plus H2 plus 2 electrons. What happens to the 2 electrons? They cancel and there's our balanced equation. Yeah, so that's exactly what's going on. Yep, okay? All right, guys. Here we go. Balance this bad boy. Here we go. Okay, guys, for those of you that play chess, you know the rules in chess, right? The move doesn't count till you take your hand off the piece. Same goes here. What I write down doesn't count till I pull the pen off the board. I'm going for 2 years in a row. You know it means business when we have to go with the very fine line. Here we go. You ready? Iodide ion plus iodate ion yields I3 ion. Balance this in an acidic environment. What does that mean that it's in an acidic environment? It means that when you're done, you will have protons, hydrogen ions, in excess, which means there will be some. We'll do one in a basic environment in a minute. You ready to go? What are the steps? Step 1, write half reactions. Guys, this is not a great example to begin with as it applies to writing half reactions because you've only got one product. But it brings up an interesting point. There is one half. You undo the. Okay. I saw Taylor and I realized, no. Taylor's down here at the bottom of his page getting ready to write this down. You want to start at the top of a new page? You want a brand new sheet of paper. So guys, step number 1, and you got to do this with me. Step number 1, and you know what, I'm going to move this over. Well, it'll be okay there. Step number 1 is write the half reactions. So this is what's going on. This is turning into this, but so is this. So the other half reaction is this. Okay, guys, you ready? Now we have a bunch of balancing to do. This is going to be my advice to you. Do these in lockstep, and if one of the two half reactions don't need to have something done to them in that particular step, rewrite it so they don't get out of sync. Watch. What is the first thing that we do? Read the steps. Balance other atoms other than hydrogen and oxygen. How many iodines do we have here? 1 here, 3. Let's balance iodines. 3I minus yields I3 minus. Okay, now let's look here. We'll deal with the oxygens later. How many iodines here? 1 here, 3. 3iO3s yields I3 minus. Crap, I already screwed up. Yep. All right. Now the pressure's off. I can make all the mistakes I want. But here's the thing. You're looking at that going, so it's just a minus sign. This will never balance. Just that one little negative sign gone, this will never balance. So this is why you skip these on the AP test. All right, well, pressure's off. Let's keep going. So now, guys, what do we balance next? It says balance oxygens by adding water. Now, guys, watch. How many oxygens do we have here? None. Rewrite it. 3I minus yields I3 minus. Okay, now watch. How many oxygens do we have here? 9. So we need to go 3iO3 minus yields I3 minus plus 9 waters. You realize I don't have another shot at doing this right for another 12 months? It's like the Olympics. You fall in the Olympics, you got 4 years to wait. I guess I got it easy. I only have a year. This is my Olympics, man. Okay, guys, now what do we balance? Read the instructions. What do we do next? Hydrogens by adding protons. Doesn't change this, but we are going to rewrite it. Now, hydrogens, how many do we have? 18. So we go 18 protons plus 3 iO3 minuses yields I3 minus plus 9 waters. Yeah. Nope. It's got to be this. Okay, now guys, this is the hard part. This is the part that you're going to screw up. I have the advantage of being able to switch colors. Now we need to balance charges. And guys, the only thing we can do to balance charges is add electrons. So we need to figure out, first of all, the charges. So what is the total charge on the left-hand side of this? -3. We've got 3 -1s. I like to write that down. Now, what is the negative charge on the right-hand side? -1. So, how do we make -3 and -1 equal if all we can do is add negative electrons? Add 2 electrons to which side? The right side. So now switching back to red, we're going to go 3i minuses yields I3 minus plus 2 electrons. You don't. Now let's keep going. Switching back to blue. I know you're thinking law of conservation of electrons, but we're not there yet. So let's try this. What is the total charge on the left-hand side? Plus 15. What's the total charge on the right-hand side? Minus 1. Now, unfortunately, I don't have 15 fingers. But what can we do to make plus 15 equal negative 1 by adding negatives? Add 16 electrons to the left-hand side. See what I'm saying? So we have 16 electrons plus 18 protons plus 3 IO3 minuses yields I3 minus plus I feel like such an idiot because I'm doing all this hard stuff right and I missed that one stupid negative sign.
Hey, that doesn't count.
No, it does, because I would have messed it up if I hadn't caught it. Yeah, but I took my pen off the board. I got to play by my rules. I know, I understand the Orem High School thing to do would be to give me a do-over and then give me a hug and make me feel better and you're okay, you knew you meant to do it right and we'll just give you an A and a diploma. I screwed up and I'm going to own that. All right. I want you to know I had that conversation with my son the other day. Coming back from Cabo, trashed his grades because he's in this accelerated math class and he got so far behind, and the rule that they have is when you take the test you're done, you can't turn in any work for the unit, and he was trying so hard to catch up and they took the test and he was still missing 2 of the homework assignments, and he did okay on the homework or the test, but because he hadn't turned in the homework he now has an A minus. And I looked him in the eye and said, Cody, don't you even think about asking your teacher to take these assignments. Don't go there. You know the rules. It didn't work out. You need to play by the rules. Imagine if all your parents had those conversations with you as well. It would be a much better place. Okay. So now, guys, you ready? Here we go. This is Garrett where we resolve the problem. So let's talk about Garrett's observation. He said, way back here, he said, if we're adding 2 here, don't we have to add 2 here? The answer is no. But why were you thinking it should have been? Law of conservation of electrons. We have to have all the electrons going in as coming out. We're just not at that point previously, but we're at that point now. But guys, before we go into that step, let me point something else out to you. This is a great place to do some error checking. Ooh, wonder if I can do this. That's moderately annoying, but it works. It's all right. We'll stick with it. So guys, look at the half reaction on the left. Where are the electrons? Product side, what does that make that? Oxidation. It's losing electrons. We don't write it as a subtraction, we write it as a product. We now know that this is our oxidation. Notice here the electrons are being gained. They're a reactant, making it what? Reduction. What happens if you get to this point and you've got electrons as reactants in both? You screwed up. Or if they're both products, you screwed up. It's got to be one of each. Yes? It's a good error check. Okay, now guys, this is the only place that I give myself permission to fall out of lockstep. Because now we need to make the electrons balance. So what do we have to do to this to make it 16 electrons? Multiply it by 8. So we have 24 I negatives, 8 I3 negatives, and now 16 electrons. That's the point. I don't need to rewrite this because I'm done playing these games. So now, guys, look at what we're going to do. We're going to bring these together. Huge opportunity to make mistakes. So here's how this goes. Bring your reactants down. 24 iodides, 16 electrons, 18 hydrogens, 3 IO3 negatives yields 8 I3 negatives, 16 electrons. Did I do that right? 8, 16, 1 I3 negative, and 9 waters. I got to check. That doesn't feel right. 24, and then I go over here, 16, 18, and an IO3 minus, and then 8 I3s. No, and I will, but okay, so I'm good. Okay, then guys, this is where we reduce. So first thing that goes is our electrons. If it doesn't, we screwed up. Then did anything else come together? The iodides over there. So bottom line, 24 iodides. Wow, sorry. Plus 18 protons plus 3 IO3 minuses yields 9 I3 minuses and 9 waters. Where? Thank you. Okay. Now, guys, one other thing we need to talk about. Do you see it? These all divide by 3. So this would actually then be 8, 6, 1, 3, and 3. And then it's balanced. Again, so this would be 8, 6, 1, 3, and 3. Yeah? Mm-hmm. What? No, you balance it at 30. So if this was a 2 and this was a 15, you'd multiply this by 15 and that by 2. Yep. Don't do fractions. What do y'all think? We're going to do one more. No, we need to. So guys, this is the next one we're going to balance. As you're writing this down, Hannah Ferguson, you have an I in orchestra. JP, you have an I in accounting. Courtney, you have an I in drama. Just a second. Garrett, you have an I in Tippett's class. Taylor Soper, you have an I in accounting. Taylor Whitlock, you have an I in Tippett's. And those are all the people with I's. Make sure you do those. Yeah, someone was...
So, the previous one said in a acidic environment.
Right, right, yes. Yeah, so let's do that because that's why we have to do this. Guys, I'm not going to go back to the previous slide, but please hear this because you're on to something important, Joe is. Guys, the deal is this. Okay, I've got to go back. Okay, so this is in an acidic environment, right? What does that mean? It means protons. So when it's in an acidic environment, it means you're going to have protons. This next one is going to be in a basic environment, and you can't have that.
So it ends up just as one.
You'll see. Here we go. So guys, the bell is going to ring on us. I just gave you all eyes, even though Skyward's dead. So you're going to be with me for a couple minutes of pride. So it goes like this. Step number 1, half reactions. Now guys, now we've got 2 reactants and 2 products. So who goes with who? The coppers go together and the nitrogens go together. So copper 2 plus goes to copper, and N2H4 goes to N2. Yeah? No, you typically, no, you never need to put phases in balanced equations on the AP test. Okay, so you ready, guys? Step number 1, balance all atoms except for oxygen and hydrogen. Done, right? If it's done for both, don't rewrite it. Now, guys, step 2, balance oxygens by adding water. Also done. Step 3, balance, oh, I'm sorry. No, I said that right. Step 3, balance hydrogens by adding protons. Now we have work to do, so I'm going to do it to both. So N2H4 yields N2 plus 4 protons. Is that okay? Now what? Now balance charges. This is plus 2. That's 0. So we would go 2 electrons plus Cu2 plus yields Cu. Is that okay? Now, guys, over here we've got 4.
Pardon the interruption. Just a quick clarification. You know, let's send out the pride month. You can really just students. Everyone didn't have pride today, but give them for them.
So then, guys, we've got to add electrons. Are you okay that we're adding the electrons to this side? This side's plus 4, that side's 0. To bring plus 4 down to 0, we need to add 4. So we'll go N2. We can read that. Yields N2 plus 4 protons plus 4 electrons. Am I okay? Again, guys, what's our error check right now? Product, reactant, we're good. So now we need to balance electrons by multiplying the left-hand side by 2. So we have 4 electrons plus 2 copper ions yields 2 coppers. Again, guys, I give myself the freedom to not write that twice because I'm ready to bring them together now. So now I like to draw a line, and then I've got 4 electrons plus 2 copper 2 pluses plus an N2H4 yields 2 copper atoms plus a nitrogen plus 4 protons plus 4 electrons. We okay? Did I do anything stupid? Okay, so then, guys, electrons go. If they don't, you screwed up the previous step. Can we bring anything together? No. Okay. So now, guys, this is why we're doing this question. Notice that this says that this is in a basic environment, but we have free hydrogens. Free hydrogens do not exist in a basic environment. So, in order to take care of that problem, we have got to get rid of the free hydrogens. So to get rid of the free hydrogens, guys, what we're going to do is we are going to add hydroxides to both sides and convert them to water. So we're going to add 4 hydroxides to both sides. On this side, that gives us 4 hydroxides, 2 copper ions, and an N2H4. Over here, that gives us 2 copper atoms, an N2, and 4 water molecules. Now we have an excess of hydroxide indicating the basic environment.
But they're all reactants, so in the end it's just neutral. So does it?
Right, and so when it says in a basic environment, it means there are hydroxides around to act as reactants.
Okay. So
Yeah.
That's,
So if it wasn't in a basic environment, this couldn't describe what's going on because there wouldn't be any free hydroxide to act as a reactant, as you're saying.
this is all before the reaction.
Right, yes, yep, you got it. Or while the reaction's happening, yeah.
So this reaction couldn't happen if it wasn't in a basic environment?
It would just happen, well, I can't say. It could, but if it did, it would happen differently. Because it would have to be through a mechanism that required protons rather than hydroxides. Okay. All right, guys, we good? So for those of you that have eyes, I frankly don't know what to tell you because it sounds like universally Skyward's not working, although I hit that small window at the beginning of third period that allowed me to not only take roll but also print a pride report. So if you have an eye, I would do the honorable thing and go check in with that teacher. But guys, it sounds like you're all excused. You've got the homework here. We'll grade this on Monday. Have a good weekend. Peace out.